Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to describe for you what I call the IFACs, which stands for Important Facts About Conductors. These are very important things to understand when you're studying Gauss's law and circuits and other types of things. So I've already written them down on the right, and now I'm just going to kind of go through an explanation of why these things are. So IFAC number one here, any net charge is on the outer surface of a conductor. So when we look at this picture here, imagine this block of aluminum. And imagine that this aluminum here, has some sort of net charge on it. And I'm just going to draw a couple, 3 or 4 here. Right? Remember that that charge repels one another. And because the aluminum is a conducting material, charge is free to move. So that those charge carriers are going to want to get as far from one another as they can. So they will end up on the outer surface of the conductor. Always, always, always true. Any net charge on the conductor will be on the outer surface. IFAC number one. Right. Another important one, and actually this is maybe the most important of the IFACs here. The electric field inside a conductor is zero, and I'm going to talk a little bit about why here. Let's just imagine for a moment that we believe the field is not zero. We believe that there is in fact an electric field within the conductor. I'm going to represent that in red. So if there were, I were to draw some electric field vectors, and I'm just drawing an arbitrary direction. If there were a field inside that conductor, the field will apply forces on charges. And remember, it's a conductor, so charge is free to move. So what's going to happen is that's going to give us a charge configuration that's going to look like this. We're going to have pluses on one side and minuses on the other. Now, when you look at that carefully, this charge configuration, plus, minus, creates its own electric field. And the important thing is realizing the direction. The direction will be opposite of the original electric field that I drew. You'll notice that, or remember that the net electric field is the vector sum. And you'll notice that that shortens those vectors. Now, in effect, what will happen is these fields will be the same length and they'll cancel. But even if you believe they won't, even if you believe that, well, the second field is maybe not as strong as the first, therefore we'd have a net field still in this direction. Well, if you still have a field, charge will continue to move, creating another electric field up, and charge will just continue to move until the net field is zero. Remember that the amount of charge that's free to move in conducting material like this is practically infinite. Maybe not truly infinite, but think about Avogadro's number for a minute. Remember that Avogadro's number, power-wise, is 10 to the 23rd power. In just a small little sample of aluminum, the number of electrons that are free to move, these are numbers like 10 to the 23rd or 10 to the 24th power. And if you think about the charge of an electron, the 1.6 times 10 to the negative 19th. Well, if you have 10 to the 23rd electrons, each one has a charge 10 to the negative 19th. You're around 10 to the 4th coulombs of charge available to move. So again, there's, for all practical purposes, an infinite supply of charge free to move in a conductor. And the charge will always move in such a way that the net electric field is zero. All right. Another important one here. The electric field vector makes a right angle to the area, or another way to say that is the electric field vector, and I'm talking about just outside the conductor. The electric field vectors are parallel to the normal. So when we look at this, imagine that there's some sort of external field. So again, in IFAC number 2, I talked about the electric field inside the conductor is zero. Well, we're talking about just outside the conductor now. Any electric field vector right at the outer surface has to make a right angle to the surface. And now, to describe why, I'm going to imagine for a minute that it doesn't. Let's imagine that we have an electric field vector that does not make an angle, that is not parallel to the normal. And again, let me draw that, what I mean by the normal vector. I like to use green for my normals. Alright, so there's a normal vector at the surface. Alright. If the electric field vector has a component in this direction, then charge will move. And remember that this is a conductor. So positive charge would move over here, negative charge over here. Now look at this charge configuration. Plus on the right, minus on the left. This charge configuration will create its own field, which is going to be this way. And remember, the electric field is the vector sum of really all fields acting. I drew that in the conductor, but I meant it like right at that point. And you'll notice that the x component of this field is to the right, but this electric field vector is to the left. So in effect, what will happen is the net field will swing something like this. Oh, I could have drawn that a little better, but let's try that again. Maybe something like this. Now, even if it still has an x component, remember, the conductor has basically an infinite amount of charge to move. So basically, we can just say, well, more charge will move. Right? Strengthening this one right here. Right? And basically what happens is charge will just continue to shift until that electric field vector is straight up. Electric field vectors have to make a right angle to the conductor. Or another way to say that, electric field vectors at the surface of the conductor are parallel to the normal. All right. Let's see. Conductor itself is an equipotential. Let's talk a little bit about why. So let's talk about, what do you have to change potential? Well, let me talk about gravity just for a moment. I always like to go back and forth between electric fields and gravitational fields. All right, so we imagine a person standing here, and you look at your coffee cup. This would be a little picture of me. I could put that cup here, here, here. As long as I put that coffee cup anywhere same height from the floor, it will have the same potential energy. This is an equipotential. The equipotentials in a gravitational situation are horizontal. That's because the electric fields point down. Or, I'm sorry, that's because the gravitational fields point down. Right? As long as I move the cup left or right, it's staying at a constant potential. If I move the cup up, I've moved the cup towards higher potential. If the cup moves down, it's moved towards lower potential. Important thing to realize, right? Change in potential. In this example, it depends on the gravitational field strength, and it depends on a change in height. Now, I'm going to call that a delta y because I usually use x for horizontal motion, y for vertical motion. In my gravity example, potential will only change if we change our height here. Potential difference depends on both these, field strength and change in height, but it's important to know the change in height here, or the distance, is the distance parallel to the gravitational field. Right, so keep that in mind. Just get rid of all this now when we talk about the conductors. All right, so potential difference, when we calculate it, in an algebraic sense, potential difference is field strength times distance. But the field strength has to be the component that's parallel to the distance. Also, because the potential difference goes down when you move with the electric field, when you look in the book, this equation will probably have a minus sign. All right. Now, this is just, in kind of an algebraic sense. We can write that in integral language too, but that's not important for this discussion. The big thing is that to change in potential, you have to have an electric field, and you have to move some distance with the field. Just like in my cup example, when my cup moved down with the gravitational field, I went down in potential. When the cup moved up, I went up in potential. Cup moves left or right, no change in potential. Right? So if I pick 2 points, let me call them A and B, inside the conductor, it's guaranteed there is no potential difference between them. Because remember, IFAC number 1, right here, no electric field inside the conductor. So this might be some sort of distance here, but there's no field in there. Right? So that thing would be 0. So A and B have to be at the same potential. Even if A and B were maybe on the surface, because we could argue that, well, there's electric fields at the outer surface. Well, that might be true, but remember, the electric fields, they may vary in length or something, but they all have one thing in common in this region. They all make a right angle to the surface. Remember, that's IFAC number 3. Electric fields are parallel to the normal. So if this is point A and this is point B, and I move over to here, as long as I stay on the conducting surface, the electric fields make a right angle, therefore no change in potential. Even if I imagine some sort of path that kind of looks like this, where I go off the conductor, well, let me kind of take that curvature or that curved path and rewrite it. You could think of it as, and let me color code this. Let me make this blue. You know, imagine we go like this way and then this way. Whoops. A little farther. And then this way and this way. So the blue are displacements. When I go from A to here, I have actually dropped in potential, but remember, we're not on the conductor anymore. When I move along this path, in my picture, I'm not really changing in potential because of the right angles. And then if I move down, I'm increasing in potential. So you've got a drop in potential and an increase in potential on the other side. You end up with a potential difference of 0 no matter what. No matter what path I choose between A and B, whether it's along the surface, inside the conductor, out here, no matter what I choose, the potential difference between those is 0. So that has, you know, an important consequence as far as, well, one, it has an important consequence as far as field lines. Get rid of some of this stuff here. All right. Any field lines, I'm going to draw these in, I don't know, I guess red. Any field lines that hit the conductor, they have to hit at a right angle. Have to, no matter what. Any field lines. I'm just going to draw some of them here. So again, these would be like electric field lines. And maybe the electric fields point something like this. Whoops. Now, the reason they have to hit at the right angle, IFAC number 3. Electric fields are always parallel to the normal. Now let's talk equipotentials, and I'm going to do those. So how about green? So remember, the conductor itself is an equipotential. The whole conductor too, inside here even. Really, I should shade the entire thing here green. And then if I were to come out maybe just a little bit, just off the surface of the conductor, the equipotential must be approximate to the shape of the conductor. But the further you get out, the more the equipotentials can vary in shape. Oops. Well, I'll just make a right angle like that. You know, so the equipotentials might look something like that, and I'd get further and further out. All right. So let me kind of run through these again. Very important to understand these things. 1, any net charge on a conductor has to be on the surface. That's because the conductor will allow charge to move. So it will repel one another to get as far away from it as it possibly can. 2, electric field inside a conductor is 0. That's just because if there is a field, charge will move and just shift in such a way that it will create its own field to cancel the original field out, if that makes any sense. 3, electric fields have to make a right angle to the surface. So this one is referring to just outside the surface of the conductor. And again, the reason, if they don't make a right angle, charge will shift in such a way that until they do make a right angle, basically. 4, as a consequence of 2 and 3, the conductor itself is an equipotential. So my advice, 1, put the stuff on a card. I guess spend a little time memorizing it, but better than that, draw a conductor and run through these yourselves. And this is an example where it's best to see these by what's called counterexample. Go through number 1 and say to yourself, all right, if I have a conductor and I do have 2 charges within the conductor close to one another, what are they going to do? They're going to repel one another. And remember, they can move because it's conducting material. And then ask yourself, so where are they going to go? 2, the electric field is 0 inside. I really suggest you just draw a picture, imagine it's a conductor, and imagine it's not 0. And if you think about that for a while, think about how the charge will behave, you'll come to this conclusion on your own. Same thing with 3, and again 4 is a consequence of 2 and 3. Now, another little qualifier I'd like to put onto this is that this stuff right here is all true for what I'm going to just call static situations. That's important. We're going to talk later on, especially in the context of circuits, where you can get electric fields in conductors when the problem's not static, and I'll explain what that means when we get to it. But for now, we're talking about static situations. So once charge has shifted around, it's done moving, then these 4 things are true. Hope this video helped describe these concepts. Have a great day.